started recently at Auckland, and he will talk about another way of a way of analyzing gravitational wave data. So please, Avi, get ahead.
Hi, yeah, as Jörg mentioned, I just recently graduated from Monash, where I was mostly just doing gravitational wave data analysis stuff, and I'm going to be working with Renata and Richard here at in Auckland. I've arrived in Auckland just on Saturday, and I've basically just been in my hotel. But I'm excited to actually see the city, and I hope that you all haven't been too affected by the cyclone. Okay, so today I'm going to be talking about gravitational wave data analysis, specifically for compact binary objects. And I've just shared a link to the notebook or the website with the notebooks, if you guys want to follow along. So this is going to be mostly just going through code and like the data analysis software pipelines that we use for gravitational wave data analysis for compact binary coalescences. So if you click on this link, you'll get to this landing page. And if you actually want to open up the code, what you can do is you can go here and go to launch in Colab. So this is going to basically open up the notebook inside Colab, and where you can actually just execute the code as we're going through it. I'd actually suggest that instead of opening this one, which is already the pre-executed notebook, maybe go to the unexecuted one, which doesn't have the output already stored. And so this will kind of like give you the plots as they come along. So I'm going to do that right now. I'm going to open in Colab. And what we're going to be talking about is like the analysis of the actual gravitational wave data once we've detected the signal. So there's quite a few steps in analyzing gravitational wave data. When you have like compact mergers, there's gravitational wave emission, and then these gravitational waves eventually reach Earth. Once they reach Earth, there's a bunch of pipelines and methods in place to try to look for the signals in the data stream. And once a signal is actually like detected, we need to try to go back to the data and try to like really extract all the information we can from the data and try to understand what the signal actually came from. Like it's almost like a Shazam app for the signal. So you want to try to decipher what the masses of the merging objects are, where it was in the sky when it merged, and how far it was, and stuff like that. And once we do that, you can also then further on do some population analysis. Like when you get like a whole slew of these merging objects, you can start doing population analyses to study population demographic information about these merging objects. So we're going to focus mostly just on the middle part, which is trying to like actually do the parameter estimation. That is like trying to understand the masses and the spins and stuff like that of the signal. So we're assuming that we've already found the signal, and we're trying to just like extract all the information we can from it. So to get started, first, let's install Bilby. So this might come up. So you can just run that. And oh yeah, if people are having issues or technical issues, please let me know. Sometimes Colab can be a bit irritating. Okay, so once we actually do that, we actually need you to do something a bit clunky. We need to restart the runtime because Colab for some reason doesn't reload the installations sometimes. Okay, so the first thing we want to do is we want to actually just do some imports. So we're importing Bilby, which is the data analysis software package that we're going to be using, and a bunch of other packages. And we're also just going to do some basic things like setting some constants and setting some random seeds and just some basic stuff. So you can have shift enter to actually run that. And this is telling you that it's running. Okay, so some more constants that we're running. Okay, so before we actually get into the nitty gritty of the code, I wanted to talk, just briefly show Bayes' theorem. So in Bayes' theorem, we have the posterior is equal to the prior times the likelihood divided by the evidence, which is kind of like a normalization factor. Okay. Yeah, and we can sometimes often write it down like in this kind of weird clunky way, where we say the posterior is equal to this pi, which is what we use to denote for the prior, times the likelihood divided by that normalization factor called evidence. Now, we won't focus too much on actually the math of this, but if you want to like get a better understanding of math, I would recommend checking out this paper by Eric and Colm. It goes into Bayesian inference specifically for gravitational waves. But before we actually get into Bayesian inference from gravitational waves, I thought we'd start off with just a simple example of Bayesian inference with some random signal. So here we have some data. And if we plot the data, so we're just doing a scatter plot of the data, we'll get something like this, right? So there's these black points are some data points, and it's like, these are some observations that we measured. And we want to try to see if there's some signal inside this. And looking at this, you might think that there is some line signal inside this, and there's some noise added to the line signal. So let's assume that the data consists of some noise and a signal. And let's also assume that the noise is just Gaussian, like white noise. And that the signal, let's assume that the signal is like a straight line. So we can code up a straight line signal, a straight line model, just like this. So we have, we input the time, and we have two parameters, which are m and c. So your slope and your intercept. And so we can define our signal model like this. Now, the next ingredient we actually need for following through with the Bayesian inference pipeline is our prior. So our prior is kind of like what we believe our model parameters could potentially be. So this is before we even look at the data. So in this case, I think that I could say that the m could be a truncated normal distribution. So it starts at 0 and it has some sigma. And I think that c could be anything from -5 to 5. So now to see what these actually look like, we can firstly just sample some of these values and look at what the values are. But this doesn't quite make that much sense. And so what instead we can do is we can just plot them. So this is known as a corner plot. This is a plot that we very often use in Bayesian inference data analysis, and it's kind of confusing to see for the first time. So this is kind of showing us histograms of the samples that we've just created. So we've just sampled about 10,000 points from our prior, and now we've plotted them. And what this shows is on the diagonal, this shows the 1D distribution, 1D histogram of M and C. And in this one, it shows the 2D histogram of M and C together. So the joint prior on M and C, and this is the one-dimensional prior. So if you wanted, you can also test this out by just doing, let's say if you wanted to just see what the histogram of your M values are, you could just do PLT hist. You could grab your samples, and then you could put your parameter in that you want to test out. And so, yeah, we see something similar again, right? So a corner plot is basically just a plot of like histograms of the parameters that you're playing around with. Please let me know if people are following. It's still, even though it's been like 2 years of the pandemic, I'm still not used to talking to just my screen. Yeah, so let me know if people are actually trying to run the code themselves or having issues or anything. Okay, so now that we've seen our we've plotted our prior, we can also try to test out what the prior would be. I mean, we can try to draw some prior samples and actually plug it into our model. So here we have some code which is going to allow us to take some prior samples. So we take our MNC samples. Is this big enough, or I can zoom in if people like, if that's easier to see. That might be easier. Okay. So what we're doing here is we're grabbing these MNC samples, and we're going to instantiate a bunch of models. So we're basically calling our signal model with all these different M and C values. And then we're going to plot these lines. So what this shows us is that the black points, again, are our data. And these blue lines represent all the random instances of our model. So right now, like, our model is kind of all over the place because this is kind of just prior samples. We haven't really done anything. We haven't actually done anything with the data. We haven't learned anything from the data. And so hopefully our inference process can help give us a better answer. Okay. So if you recall that okay. Can I get a thumbs up or something to like let me know if people are following, or if I should go slower, or oops. Okay, cool. So recall that our assumption is that the data is made up of some noise and a signal embedded in that noise. Now, we also assume that the noise is just normally a Gaussian distributed, right? So we can write down that the noise is just kind of some normal distribution. And you can also write down the noise is equal to the signal. Oh, sorry, I think I messed this up. This should be the data minus the signal, right? Yeah, oops, whatever. I'll fix that. And we can now write down our likelihood like with this information. So we can basically write down our likelihood with the information that, you know, like the data minus the signal is going to be just random noise, random Gaussian distributed noise. And so we can write that up in our likelihood. And in Bilby and other packages, these are often very like these, you can all find these in like a Gaussian likelihood. And so we instantiate that, and we want to actually test out if, you know, like if things are working. So you can actually just put some random model parameters into your likelihood, and then you can test it out. So right now we're just printing out our likelihood. Cool. So we have some number. And so things seem to be working. There's no nans at the moment. Okay. So before we actually get like so now that we've established our likelihood, our now we have all our ingredients. Now we have our prior, we have our likelihood. We can also get the evidence, which is just, you know, like summing over all potential values of our parameters. So now that we have all these ingredients, what we can try to do is we can actually try to brute force compute our posterior. So make a grid of your theta values, so grid of M and C values, and then compute the prior and the likelihood at all those grid points. So let's go back here. So what this is doing is that this is going to load up a grid of M and C values, and this is just some code to plot the grid. So let's take a look at what we get. So this is a grid of, I've asked for 100 by 100 grid. So there's 100 M values and 100 C values, right? And so this is kind of filled up our parameter space. Now let's compute the likelihood, the prior, and posterior at each point. Now to implement our posterior, it's actually quite simple because we just need to, we can just compute our prior and likelihood now that we have that. And then for posterior, since we're using logs here, we can just add up the log prior and the log likelihood. And then finally, the evidence can be computed by just summing over all those values that we previously computed. This is kind of the normalization factor for the log posterior. Okay, so let's see what happens when we actually compute the log likelihoods in the posterior for each of those points. So these are 3 plots of the prior, the likelihood, and the posterior. So we've now colored those grid points, those M and C grid points, based on the prior. So the higher the probability, the yellower this plot is. And so the prior is kind of the MNC prior, joint prior is showing that, you know, it's preferring M values that are low, and the C is uniform, right? And when we actually compute the likelihood, we see that there's some peakiness going on in the center, like near C of 0 and M less than 1, right? And the posterior is kind of just multiplying these two together. And in this case, the likelihood is kind of dominating, and we kind of get back the same, we kind of just get back the likelihood. Okay. So now that we have these distributions, we can actually also compute what's known as the marginal posteriors. So in this, what we're doing is we're just integrating out to calculate the marginal posterior on M. So that's like actually trying to see what value of M do we predict. We can actually integrate out C. So this is kind of just so to do this, you can actually just take your posterior array. So here we have our okay, so to get the marginalized posterior, what we're going to be doing is we're going to select subsets of the entire grid, and we're going to kind of just go row by row and sum up what the likelihood is at each of those. So we want to calculate the sum of all the likelihoods here, and then all the likelihoods here for each of the M's. And so once we do that, we can actually plot the marginal posterior. And so we see that, you know, there's some peaks at M of 0.6 and C of negative 0.4. And now that we have this, we can also try to plot our most likely posterior samples on our data. So here we again plot the data in black, and this time the models in purple, and we see that we're actually fitting the data a bit better than previously. Okay, now, does anyone see the problem in actually doing this in a brute force method? What would happen if we increase the parameter space to 15? So right now we just had 2 parameters, right? And so we had 100 by 100 grid, and that ends up being like 100 times 100, so 10,000 data points that we have to compute the likelihood at. So what would happen if we have 15 parameters? Does anyone want to? I can't actually see the chat, so if anyone's typing in chat. Wait. Yep. Yeah, so you'd have a lot of points, right? So it's kind of really hard to do this in a brute force method when we have more than a few parameters. And so this is when we start using different types of methods to kind of explore the space. So instead of a brute force trying to compute it at each grid point, what you can try to do is you could try to sample the parameter space. And there's a bunch of methods that exist to do this. In fact, Renata in 1999 published a paper on using MCMC in gravitational wave data analysis. I think Renata was one of the first to kind of probe this area. And since then, we've been looking at all these different methods to actually sample the parameter space. And what these samplers try to do is, instead of actually, you know, computing your likelihood at each of those potential grid points, it tries to find the regions where the probability is higher. And by doing this, it tries to estimate what the posterior is. And so it tries to like walk around the parameter space and try to estimate the posterior. So this is what Bilby is kind of made to help do. So Bilby is a software package that can, you know, help us try to actually set up our gravitational wave data analysis. But you can also do some other Bayesian inference with Bilby. So here we're going to use Bilby to sample this parameter space. So we've provided the likelihood, we've provided the prior, and we're using a sampler called Dynasty. So Dynasty is a nested sampling, an implementation of a nested sampling algorithm. So it kind of draws circles around regions of probability, and it tries to go towards the regions of higher probability. That's kind of what nesting sampling is in a nutshell. And so we can run this, and we'll see a bunch of logs that are coming out from
Avi, sorry to interrupt, but I actually get an error when I ran that. I got name error. Name out directory is not defined.
Oh, okay. Have you run this top cell up here? I think this is like
Yes, I wonder if I missed that one.
I'm so glad that someone's actually following along.
Oh yes, I missed it. Thanks.
No worries. You can also just like write it in here. All this is going to do is it's going to like create like a folder where all your samples and stuff are going to be saved.
That looks like it's working now. Thanks.
Cool. So let's take a look at the logs that we actually get from running this. So we see some logs saying that, like we're running, this particular analysis, and the output will be saved here. We print out the priors just for, in case you look back at the logs at some point. We print out what type of likelihood we're using. Okay, so we see that the noise evidence is a NaN. This is because we haven't actually coded up a noise model. And we see that the single likelihood evaluation took a microsecond, around a microsecond, which is pretty good. So it's quite fast. And there's something about checkpointing. It's going to be checkpointing every 600 seconds. I guess in this case, because it already finished, it's quite fast. But in situations where sampling can take a long time, this is quite useful. And so we see that, we've sampled about 3,900 points, which is actually fewer than what our brute force method used. Our brute force method had, I think, something like 10,000 points. And we have an estimation for the evidence. So that's the normalization back to the probability underneath the posterior. And yeah, so now that we have these results, we can try to plot them. So let's plot a corn plot, like the ones that we were looking at earlier. Okay, so yeah, we see that we have some distribution for M and C, and we also have some marginal distributions, and we see that we get some values, estimated values for these as well. Here, the green line is I plotted the prior on top of the 1D marginal distributions. So here you can't, this was a truncated Gaussian, but because the axis has been kind of shrunk to the regions where the probability is the highest, you can't see the entire prior. But if we extend it, let's try to see if we can actually extend the ranges. So I think it's something like this. So let's extend the range to -1. This might break. Okay, no, that looks good. So now we can see our prior as well. So we see that the prior was a truncated Gaussian, and the prior for C was a uniform distribution. And we see that our posterior is quite different from the prior, which is good. That means we're actually learning something from the data. Cool. So now we can actually also, because this was like a synthetic example, I also have the true values. So you can try to plot the true values on top of this posterior and see how we've done. Okay, so I've plotted the true value on the data with our model posterior is also plotted on the data. So we see that we're kind of getting, the true values within our 90% credible interval. So that's kind of like the where 90% of our posterior lies in this region. So our true value is, our analysis seems to be working, which is good. And finally, we can also compare our our brute force method with the sampling. So we see that there's quite good like comparison between the brute force and the sampler methods. And we see that the evidence is slightly different. We could actually go and like compute the evidence by hand in this case, but I haven't done it. But things seem to be working, which is good. So hopefully now you can trust the sampler, even though it's not like computing the probability at each grid point. So now that we've gone over this example, it's kind of which is kind of hopefully introduced these concepts of how we can do Bayesian inference using Python and Bilby. Let's move on to actual gravitational wave signals. Any questions up till this point? Have you tested other non-Gaussian likelihoods? Not for this, but there's quite a few different types of likelihoods that Bilby has. So if you wanted, you could try to play around with it. So I think if we do import, I honestly forget where it's saved, but if you check the Bilby documentation, there's a slew of different types of likelihoods, and you could try out a different likelihood if you'd wanted. If anyone wants, you can also try out, like test out different priors and stuff, and hopefully things should still work. Okay, so moving on to the next section. So before we actually get into parameter estimation with CBC signals, CBC meaning compact binary coalescence is a short form for compact binary coalescence, I wanted to go over the models that we actually use. So in this scenario, we often have between like 15 to 17 parameters, sometimes even more. So we always have two mass parameters. So this is kind of to constrain the mass of each of the component black holes. Sometimes we reparameterize this in other types of mass things, such as like mass ratio, which is like the ratio of the heavier black hole divided by the smaller, or the other way around, depending on your preference. You could also use things like chirp mass, and you could use something like the total mass, which is the sum of the masses. But normally you need at least two mass parameters to help constrain the masses of the black holes. Then there's 6 spin parameters. So there's 3 for each black hole that represent the x, y, z coordinates of the spin vector. You can also write it down in Cartesian coordinates. So you'd have 6 spin parameters. You could also, if you assume that your black hole is not actually going to be tilted at all, in that case, you can only you can ignore the angles that the black holes might be spinning in, and you can just focus on like the spin magnitude. So if it's spinning really fast, or if it's not spinning at all. There's also, if you're analyzing data with a neutron star, you could also add in tidal deformation parameters. So that's kind of how squashed the neutron star gets as it comes close to the other compact object. And people have also looked into looking at eccentricity of the merging objects. So you could use things like the eccentricity in the argument of Perigastron to actually try to figure out what type of orbit the compact binary was going through before it merged. And then there are 7 other parameters that are kind of dealing with the extrinsic nature of the system, such as like the distance that it is from Earth, the time at which it arrived, the signal arrives, the location in the sky, and stuff like that. And okay. Okay, so I'm going to look at this section on here because it looks a bit better here. I think the LaTeX probably hasn't rendered. Okay, so we've been over the mass parameters. There's 2-dimensional mass parameters. Oh yeah, another thing that I kind of skipped over was that the mass of the black holes that we detect is actually redshifted. Because the universe is expanding, The same way as, light from distant stars gets redshifted as it reaches us, the gravitational waves also get redshifted. And so we need to account for that. So the mass in the source frame, which is where the black holes are actually merging, versus mass in the lab frame, which is in our detectors, is actually different. And so we need to try to account for that. And we often try to use, you can try to use different types of cosmology to try to figure out what the source frame mass is. Okay, and the spin is, I think so I think I mentioned this. So you can use all spin parameters, like if you provide some angles to your black hole spin orientations, but you can also just kind of allow them to be aligned. So there's no angle, so they're kind of lined up, and just look at how fast they're spinning. And in the case for isolated binaries, which are just binaries randomly isolated in space without anything else affecting them, it might be an okay assumption that they have small misalignment. They might get slightly misaligned from supernovae from when their stars blew up to then turn them into these compact objects. But we expect that systems inside, things like globular clusters, nuclear star clusters, or even AGNs can have much more spin, because they have other dynamic encounters which can try to whip the spin around and stuff like that. Okay, and I wanted to show you all this animation of two precessing black holes to kind of explain what's the idea of precession. So when your black holes aren't actually lined up, when their spins aren't lined up nicely, so in this case, the black hole spins are kind of in the plane, they'll start precessing in their plane, their orbital plane will start precessing. And so this is kind of an animation that you can make using a package called SurfinBH, written by Vijay Varma. And that kind of helps you visualize these signals. And it's kind of nice because you can also see the strain plotted along this, and you can see the different points of the mergers. You can see the in spiral versus right now it's entering now it's in the ring down phase, and it's been kicked away. Okay, so hopefully that gives you an idea of the different parameters that we're dealing with. And so now let's try to plot the waveform itself. So I'm trying to create a black hole with a binary black holes, emerging binary black hole system in which the masses are 20 and 25, and I've hard coded some other values right now. I think it's a non-spinning black hole. So yeah, it's a non-spinning black hole. These won't be used because it's these won't be used right now. I've just kept them here just for to remind you that you can use these. And we've set the distance to be 1,000 megaparsecs, and we've zeroed out most of the other parameters. Okay. So in this case, we get some signal that looks something like this. So we have the plus and the cross polarizations plotted on top of each other. And you can see that this is like a signal that lasts, a few seconds. But you might wonder, what actually happens when you start changing some of these parameters. So if people have been following along, you can now try to play around with this. And so here we have some plots of what happens when you actually change the chirp mass. The chirp mass was one of the mass parameters that we looked at earlier. And so you can see here when the chirp mass is 60 solar masses, it's a really short signal. And as you start decreasing the chirp mass, you see that the signal increases in length. And this is kind of why when we analyze binary neutron star signals, which have very small chirp masses compared to these merging black holes, their signals are much longer. And so we need to analyze them with a larger data set. Does anyone have any questions at this point? I'm checking chat.
Is there a mass, like curve mass or even individual mass limit, upper limit for the model?
So yeah, there I think that, so firstly, there's probably going to be some, I mean, there is some like astrophysics that like, determines, like what these like, limits for these systems could be. In these waveforms, there's some like upper limits that you need to kind of like, account for, and like when you actually start using this in your analysis. So the current waveform that I'm using is called IMR phenom PV2. So what this stands for is in spiral merger ring down phenomenological version 2. It's kind of a weird name. But this, I think, cannot, like you cannot add in eccentricities. I think it doesn't do well with very high mass systems. So let's try to break this. Let's try to like make it like a 500 and a 500. It might produce something, but I wouldn't trust it. So yeah, what even is this? So yeah, you need to be like cognizant of your the model that you're using, and so you need to read the paper and make sure like where do they think that it's like trustworthy and stuff like that. So oftentimes you see that they can go up to like a maximum spin or something like that, and so you need to be aware of things like this.
So can I? So yeah, that's good answer. Thank you. So can I say, well, can I ask you whether you've tried maybe putting in galactic white dwarfs in? Do they have any waveforms to describe that?
I think they do, but this is probably not the one. I'm not sure if IMR phenom PV2 will be a good yeah.
Right, it's not too bad. It's monochromatic, isn't it? It's not merging, so
well,
that looks all right.
Well, I've also hard coded the duration. So let's make the duration like something like 128 seconds, probably longer, but oh yeah, I don't like I feel as though we need to like check the papers to see like what actually went into making this, and like where the creators of the waveform trusted to. Does that kind of help?
Yeah. Thank you.
Yeah, no problem. Okay, I'm gonna fix this because I think I need this at some point later on.
Avi, there's also a question in the chat.
Oh, thank you. Was this have you tested other non-Gaussian likelihoods?
Yeah, that's the one I saw.
Oh, I think we spoke about this. I think this was in regards to the linear regression example.
Yeah, I see. Okay.
And so yeah.
Okay.
Thanks for keeping an eye on the chat though. Cool. Where was I? Okay. Just want to test that I haven't broken anything. Okay. So yeah, if I was going to give people some time to actually play around with this and try to like investigate what happens. So I've also made some example like interactive animations, so you can try to play around with like changing what happens when you change your spin. And so do people want some time to actually play around with this to like get a better intuition for some of these parameters, or should we keep going? Oh,
Keep going.
all right, keep going.
Yeah, Avi, you decide yourself when is the best time for a break if you ever want to have a break.
I'm fine with whatever. It's yeah.
You have planned for a full 2 hours, right?
Like it's been like, I think I was trying to go a bit faster because I know that the numerical relativity labs are going to be after this. So
well, that is true, but you shouldn't go too fast. But yeah, as whatever is okay with the audience is fine with me. So just continue.
Continue. Okay. Okay, maybe we can come back to this. I was gonna suggest that if people wanted to play around with trying to see what happens when, like say that you fix your fix one of your, or like fix your spin parameters and start playing around with one of your black holes spin angles, what happens. But I think that we can come back to this. And now that you have these notebooks, hopefully you can come back to this on your own time if you want to investigate this. Okay. So now that we've played around with the model, I was going to try to get into parameter estimation with, these models. So gravitational wave data analysis with these models. So again, let's actually simulate in this. Let's start by just making like a mock scenario. So we're going to simulate a signal and we're going to plug it into detector data. And then we're going to try to see if we can actually extract like some of these parameters from the data. So here, what we're doing is we're specifying the duration of the signal, the sampling frequency of the signal, so like how often we have data points, and the minimum frequency of your detector at which it's sensitive. So we set the sampling frequency to 1024, and we set the minimum frequency to be 20. And so I'm going to be injecting a signal with these parameters. So it's 36/29 merger, and it's very slowly spinning, and it has some sky position and some distance. Cool. So let's try to simulate the signal and let's plot it. Okay, so this is the signal we're going to be injecting into detector data. So Bilby has a nice interface to actually like grab the detector data and make plots and use it in analysis. So the way we can do this is we can ask Bilby to create a list of interferometers. So in this case, we have the Hanford detector, but you could also add in things like Livingston, so the L1 is for Livingston, and you could also add in Virgo if you wanted, and Cagra and stuff like that. I think we're working on adding Lisa, but that's still going to be a while, I think. But we do have some of the other ground-based detectors, like we have like mock design sensitivities for 3G and stuff like that.
Avi,
yeah.
There's a question in the chat.
What is the noise you're injecting into? So we're going to be injecting into like the detector noise at design sensitivity. So here, maybe I'll just plot it. Okay. Oh, and it's basically just Gaussian noise. Sorry, if that's what you're asking. Just stationary white Gaussian noise. And so what we've done is we've created an interferometer. Then we're trying to like set like a baseline strain that's created from just the PSD, just like the design sensitivity. So if you actually remove this line and plot this again, I think this might break, but okay, I can't actually, I guess we can't see the difference because the signal is very here. Okay, yeah, so here in this case, the signal is very faint when we're injecting it. So it's like okay, it's not very faint, it's an SNR of 12. Does that answer your question, Renata?
Yeah, I was just mainly wondering whether you're injecting in real observed LIGO data from maybe the third observation run, or you're just simulating from a certain power spectral density of LIGO or Hanford?
Yeah, so in this case, we're just injecting into the certain power spectral density of LIGO Hanford, and it's the design sensitivity.
Yeah, that answers my question. Thanks. Thank you.
Cool. Okay, so yeah, we've injected the signal in this data. The orange line actually represents the PSD, or the power, the ASD, the amplitude spectral density, and this kind of like our estimation of the noise in the detector. And the more noisy looking lines in the background is the actual data in the section that we're trying to analyze. And so we're going to be trying to use the this ASD to try to like whiten out to remove some of the noise that's in the data that we're analyzing. So actually, this would be a good time to talk about the noise in the detectors. So Jade spoke about this a bit in her talk, and I think Susan also spoke about this, and so did Dan. So we're plagued by a lot of noise in the detectors, and comes in like you can think of like in 3 varieties. So there are these glitches, or these are random like kind of sporadic bursts in the detector data, and these could be from things like woodpeckers pecking on the arms. It could also be from people opening, shutting fridge doors, and there could be like a lot of things that cause these random glitches. And then there is the white noise. So this just comes from all the stuff that Dan was talking about in Dan's previous talk, where there's things like your shot noise, your thermal noise, and suspension noise from like your mirrors vibrating. Well, actually, the suspension noise causes these lines in the frequencies. So there are these like lines that are in the data stream. These are called like, I think these ones are the 60 and the 120 violin mode. So these are, I think, from the pendulum shaking a bit. I might be mistaken. I sometimes forget what the lines are for each of these. But yeah, so to try to account for all these types of noise, there's different ways to do it. Like for the glitches, you kind of have to do things like actually just take the data and whiten that section out with the glitch. And there's nice ways of doing this. You could try to use like a model of the glitch using something like Bayes wave to try to delete the glitch itself. But these are sometimes computationally expensive. And so glitches are really irritating, like to deal with. And sometimes you have them in your signal itself. I think in 17017, the binary neutron star detection, there was a big old glitch in the middle of one of the detectors. And they had to actually go in and try to remove that from the data. Okay, now to deal with the other noise in the detector, which is like the Gaussian white noise, or I guess it's not actually white noise, but it's it's noise that we have to try to account for. And so what we try to do is we try to compute this thing called the power spectral density, or the amplitude spectral density. And there's a couple of ways to do this. One of the ways to do this is by taking a long chunk of the data. So you can take the long chunk of the data after the signal or before the signal that you think exists. And then you can kind of like chunk that long section up and then try to average over that to try to see what the average noise property is over like some period of time. So oftentimes when it's something like a 4-second duration of a signal, what you do is you look either before or after, so off the signal where you expect the signal to be, and then you grab like something like 32 times the length of what you expect your signal to be. So if you expect your signal to be 4 seconds long, you grab some chunk like right after, right before it, that's much longer, and then you chunk that long chunk into smaller chunks and average over those chunks. Does that kind of make sense? Okay. a better way of doing this is actually to use information about the instruments and about, like all those different noise properties that Dan was talking about. So there's software packages such as Baseline, which actually goes into like modeling some of these, noise features and tries to actually compute like a estimation of your noise. But these are often quite expensive to create. And so sometimes what ends up happening is that we analyze using the first method, which is, quite easy to, like it's easy to make these because you can easily just get detector data from before or after, and then you can average over that. And then you do your analysis, and then later on we come back and we do our analysis again with a better model of our noise, so a better PSD. Okay. Okay, and then there's also the lines that we spoke about, like those violin modes. What we can do for these is we can just kind of like notch out that section of data where the lines could exist. And yeah, so these are like the main types of noise. And so right now we're just going to be assuming that the noise is like stationary Gaussian noise, and we're going to use the PSD to help write in some of the data. Okay. So now we can, now that we've looked at the PSD and we've looked at our, like, and we've created our data set that we're going to be working with, we can also try to actually create a prior. So normally in our analyses, we have to, sample over all these different parameters, but for the sake of time and like so that we can get to the numerical relativity labs, we're not going to actually sample over all these parameters. In fact, we're only going to sample over one parameter, which is chirp mass. And we're going to set delta functions and all the other priors.
Avi, you don't have to rush because as far as I can see, Chris is on his way home and tells me that he will be home around 4:15. So you do have enough time.
Oh, well, I'm like already halfway through. But maybe
yeah. No, that's fine. So but don't rush.
Okay, that's good to know. By the way, can I get like a can people like give me a thumbs up if they're actually like trying to follow along the code, or if they're just watching me?
Mostly watching you.
Okay. Okay, cool. So we have a few code followers, and I hope that things are going well with the people who are actually executing the code. Have people run into any issues or bugs?
Okay. I haven't. It all runs very well for me. Thanks.
Oh, that's great. Okay, cool. Yeah, I'd initially, since I was planning on coming, since we were going to do this in person, I'd initially kept a lot of the code, like a lot of like code to be written by the workshop attendees. But I thought that because it's an online version, it'd be easier if the code is already all there. Okay, cool. Where were we? Okay, yeah, we were talking about the priors. So in this case, we're going to be setting delta functions on some of our parameters. We're going to like all parameters other than the chirp mass. And so another thing I want to point out is that let's actually take a look at some of these priors. I'm going to open up a Bilby prior file. So bear with me while I try to find it. And since we have time, I thought it would be nice to actually okay. So I've opened up a prior file in Bilby, so I'm going to share it in chat. I just saw, yeah, the little dogs. I kind of like corgis, so I got these corgis to run. You can like, I think there's a plugin which you can set different type of animals to run. Do we always use linear or some? So Jerry has asked a question, do we always use linear regression to estimate the parameters, or are some parameters better with other forms of estimation? So I will say the linear regression was just like a kind of like an example. We do not use linear regression. I think we'll get into like the actual how we actually do our analysis in a few seconds. Okay. So yeah, let's take a look at the prior. So firstly, we see that there's these 4 mass priors, right? But the first 2 are actually just constraints. So this is a constraint on mass 1 and mass 2. And we're actually sampling in mass ratio and chirp mass. So what the constraints are doing is that they're telling your sampler that do not step further than, don't look further than these ranges, because we don't expect our black holes that are merging to be within these, beyond these ranges. But we're not actually sampling in mass 1 or mass 2. We're actually sampling in mass ratio and chirp mass. So notice that our mass ratio's minimum is set to 0.125 and the maximum is 1. And so this is, I think, due to the constraints on the waveform. So I think someone was asking earlier about, where do you trust the waveform? And I think that some waveforms break down lower than this for a chirp mass. I mean, for a mass ratio. So there's other waveform models that are made for extreme in spirals, but the one that we use for compact binary coalescence analyses, we normally don't deal with those. We also haven't seen things that are too extreme mass ratios yet in the gravitational wave data sets. So I think it's okay that we've been doing this. Okay, now the chirp mass. So the chirp mass is from 25 to 100. And we also note that this prior isn't something like uniform in, from this range. It's something called uniform in components chirp mass. So this is kind of a weird name, but what this is actually saying is that this is going to be sampling in this parameter space, but then at the end of the analyses, you're actually going to convert back to a prior which is uniform in component masses. So we found that there's some papers talking about how it's actually more efficient to sample the parameter space using chirp mass and mass ratio. Using chirp mass and mass ratio, you can explore the mass parameter space better than you can if you were just using mass 1 or mass 2. And so what we do is we try to sample in this, but having chirp mass and the mass ratio are kind of unphysical, astrophysically, they're pretty weird. If you take a look back at the equation, this is the chirp mass equation. It's a very strange combination of M1 and M2, but it's easier to actually sample in this because you can write your waveform, you can write your gravitational wave model using this. And so you can directly measure this chirp mass. But yeah, having a uniform distribution in chirp mass doesn't really make that much sense. And so instead of having a uniform distribution in chirp mass that we sample from whatever this distribution is, but at the end of your analysis, you convert back and assume that you're you convert back to uniform mass 1 and mass 2 priors. Does that kind of make sense? I know it's kind of a confusing concept, but I just wanted to introduce the idea of, you can sample with one prior, but then at the end of your analysis, you can convert your prior. So you can do some gymnastics to try to change what your prior was. Okay, I will take silence as that it was kind of understood. But please stop me if it wasn't. Okay. So the luminosity distance. So this is something that we've said uniform in source frame. So what this is doing is that it's trying to account for the fact that we're basically trying to look because the universe is expanding, you need to try to account for that in your luminosity distance prior. You basically expect to see more things that are further away. There'll be more black holes that are further away. Does that one make sense? Okay. So now these ones, this is your declination and your RA. So these are like sky positions priors. And so we kind of keep these to be uninformed. So like all of these are uninformed, but we don't have any special kind of prior for this. You just have like a cosine prior for your declination and a uniform prior for your RA. And the rest are also kind of just uniform. So hopefully that kind of makes sense of what type of priors we use. So let's go back to our actual inference. So, okay, so in this problem, we've put delta functions on all of the parameters other than your chirp mass. And we've set the chirp mass prior to be very narrow around the injected value. And this is kind of just to help make it a bit faster in your analysis if you actually want to run it on your computer right now. So let's run this. So this is creating that our set of priors. And I'm not sure why it's taking, so okay, it's done. Okay. And now let's make some plots. Okay, so I guess we only have one plot to make since we only have one prior right now. So this is the chirp mass distribution. So note that it's not actually complete, it's not uniform right now. And even if we increase this, it won't be uniform because it's that weird prior that we've coded up. And it'll be uniform in component masses when we undo the prior at the end of the analysis. Okay. Now, the next ingredient we actually need is the likelihood. So the likelihood is, in our case, is not the same Gaussian likelihood. It's going to be the Whittle likelihood. And the Whittle likelihood is a likelihood that's used for time series data. So it's used for looking at, it assumes, again, that the noise is Gaussian stationary. And in our case, what we can do is we can compute our, so here we have D is our data, H is our model, so our waveform template. And so this D minus H should be just like a Gaussian noise. And then we divide it by the PSD to try to make the noise, to make the noise white. So it's not like moving around. And we want to do this for all points in frequency between 20 and 2048, wherever your minimum maximum frequency is for your analysis. And then we want to do this for all of the detectors. So
there's a question.
Thank you. So I think that people have looked into, Kate wrote in the chat, it seems that the priors are bounded and quite informative from the domain knowledge. I wonder if the quasi Monte Carlo method has been considered. Instead of sampling, we integrate over specified grid points. So I think that people have looked into this, and there is actually more people coming up with ways of doing primary estimation like on the fly. So like doing primary estimation in like less than a minute using kind of like these grid point kind of methods. But yeah, I'm not too familiar with them at the moment. But yeah, like if you look at, if you go to like ADS and just search for parameter estimation in gravitational wave for LIGO, there'll be like, like a lot of papers, and even the last 2 years just talking about how they can improve the parameter estimation process within like, by another factor of like, a few minutes and another few minutes. Yeah, I'm not sure if that doesn't really answer your question, but
it was yeah. I looked at the prior and yeah, I thought about it, and I wonder whether you've considered and whether you've tried different methods, and whether there's a good reason to do sampling. I mean, sampling is quite straightforward, and the problem of a integration over grid points can be quite weak, can be quite challenging when you have a very high dimensional problems. So I wonder whether you come back to sampling because of that, or yeah.
Yeah, I'm not sure honestly. So yeah.
Yeah. So yeah, but thank you. Thanks for the answer.
Yeah. Cool. Okay. So to actually instantiate this with likelihood in Bilby, it's coded up in this thing called the gravitational wave transient likelihood. And all you need to pass in is the interferometer. This contains all of your data, your analysis data, and your PSD. And then you need to pass in your waveform generation model. So this contains all the information about, how to generate your waveform. So if you ever wanted to, like create your own waveform, you need to hack this waveform generator. And if you want to like create a new method of like, like someone was trying to do something with modeling the PSD on the fly during inference. And so they would need to hack this object. Okay, so let's run this. And so now we have our likelihood object. So now we can actually run our sampler. And so I think that someone had asked earlier, like why, do we always use linear regression to estimate the parameters, or are some parameters better with other forms of estimation? So we're not actually using linear regression here. What we're doing is the priors are going to tell the sampler how to explore the parameter space. So there's a lot of different, in our case, there's, theoretically there would be 15, but we've chosen one. And so you'd want to be able to like look at all these different points in parameter space and try to figure out where the likelihood or where the posterior probability is the highest. You want to try to go towards the region where the data tells you. And so what the sampler does is that it takes your likelihood and it takes your priors and it uses the prior to start exploring the space. And it looks at what the likelihood is at each of these points in space, and it tries to go towards regions of higher likelihood. If you're familiar with machine learning, it's almost like you could think of it like gradient descent. So you have this this multidimensional likelihood space, and you're trying to go towards the region which is of the highest likelihood. Does that make sense? Okay. Cool. So in this case, I've specified some other things like endpoints, nlive, and walks. So what this is telling us is that this is like setting some additional settings in your sampler. So I honestly think that sampling is almost like an art form. And so, coming up with these sampler settings is sometimes a real pain in the butt. And so what we often do is we try to max these out. So, people do things like use, 1,500 points and then have a really large walk. And so what this is telling is that for each point, you want to walk how many points and stuff like that. Okay. And okay, I'm going to undo this because we don't want this to run for a long time. So I'm actually going to try to run the sampler, and I'll stop it before, because it'll take too long. So I'm running it just so we can see some of the logs. So again, we see the same logs. We see that, we're running, here, and we're using this version of some of these packages. These are our priors. Yeah, you can see that everything is like a delta function. Oops, what happened? Okay. Oops. Okay. You can see that we're using this gravitational wave transient, and this time the likelihood evaluation is much slower compared to previously. And so the reason for this is because the likelihood has to, I think one of the most expensive points of the likelihood evaluation is actually the waveform model. So computing those waveforms is not as easy as computing a line, a straight line, right? You have all these parameters, and then you have to pass it to this, package that generates the waveform, and then it takes a lot of time, and that's what actually brings down that's what makes the likelihood evaluation so slow. So previously it was around a microsecond, I think. Okay, and so people have worked on different ways to actually make this likelihood evaluation faster. Like some people have looked at doing something known as reduced order modeling, and what that does is that it actually makes like a set of waveforms, like a basis set of waveforms. So you basically you take your prior, and then you try to like generate a bunch of waveforms from it, and then you see if you can use those waveforms as a basis itself to create new waveforms. So this kind of like allows you to skip over calling the actual the waveform package or whatever, and it makes it much faster. So there are some papers out on this, and this concept is known as reduced order modeling. And we use it quite often for when we want to analyze long duration signals. There's some other work that's been done known as heterodyning, and that's just another way of trying to make the likelihood evaluation a bit faster. And I won't go into that one as like, because I think that's a bit more confusing, so I won't discuss that for right now. Okay, but let's take a look at these logs. So while this is running, we see that we have a couple of these logs that are printed out, right? So firstly, the one the furthest left is the number of iterations. So right now it's in this 291st iteration. This is the time that it's been running for, and this is how long it's taking to run each iteration. And these are some things that are to do with nested sampling. So I think bound tells you how many bounds is created in that particular iteration, or like and NC is I think NC is the number of calls in that particular iteration, and ncall is the number of calls altogether. So it's already made 2.5 more than a few thousand calls to our likelihood. So my laptop right now is really churning and doing some hard work to try to figure out what our posterior is for the chirp mass. Okay, and this next one is efficiency. So this is telling us how efficient our sampler is. So this is saying that it's 11.4% efficient. That's actually not great. It's like it's saying that it's probing all these different points in parameter space, but it's only accepting a very few points in parameter space. And so all these other evaluations, all these other calls are kind of wasted. And the next one is log Z ratio. So this is to do with, so it's something to do with the evidence ratio. I'm not too sure honestly about this one, but this next one is the D log Z. So this is trying to, this is at each step of nested sampling. What you can do is you can actually evaluate what your current evidence estimation is. And your D log Z is looking at how much this is changing in each step. And this is actually going to be our termination criteria. So we're going to allow this nested sampling algorithm to keep running until the D log Z reaches less than 0.1. And so once the once the evidence is no longer changing that much, we're going to stop our analysis run. Okay, this is going to take ages, so I'm going to stop this. And what we're instead going to do is we're going to skip sampling, and we're going to download like some results that I ran yesterday. Okay, so we've downloaded, so just pretend that we ran this right now, and this is now our results. So this is going to be our results that we're going to be working with and looking at. So now that we've finished sampling, we can make some plots. So at the end of our sampling, we often do these type of things, like we do some post-processing steps. So firstly, one of the post-processing steps is to try to undo our priors and the undo our weird chirp mass priors, and then put them back in the uniform and component mass priors. And we also do some additional computations, like we generate this conversion function here is telling my sampler that at the end of the run, compute some of these additional gravitational wave parameters. So what this does is that this takes in like our posterior samples, so our samples from the posterior, and then it computes some additional parameters. So initially, we only had the parameters that were in our prior, but then we want to actually look at other parameters such as like the something like the chi effective, which is like some other spin parameter and things like that, right? So what we can do is this kind of helps us do that, helps us compute all these other additional parameters. Okay, so let's make some plots now. So what we're going to do now is we're going to try to plot the posterior for mass 1 and mass 2, and we're going to overplot the true values of overplot our true values for mass 1 and mass 2. What we're also going to do is we're going to compute what the waveform is from our posterior, and then plot that over the detector data. And I think the second one is taking a bit of time. Okay, but are there any questions while this is running? Chat.
There is one in the chat.
Thank you. Yeah. Are there any limitations to this kind of inference? Any types of events where Bayesian inference is unwieldy? Yeah, the problem is that this takes way too long. And so part of my PhD was trying to help make this faster. So, you know, like people have done all sorts of things. Like, you know, some people have tried to like, you know, so I've tried to like set up a way to do this using the message passing interface, like in using MPI on a cluster. So you can use a supercomputer to actually do this. But there's other ways of doing this that make it a bit faster. And but I guess that's not answering your question. Yes, Bayesian inference is, you know, like it takes too long, and so it's quite expensive because of that. That's one of the main limitations. There's also cases where sometimes your sampler fails, like your sampler might not be able to actually, you know, like say you have a very, very loud signal, and you know, like that, you know, like it's very loud that, you know, like, or it's so loud that the likelihood space is very peaky, so it's like very sharply peaked. And so some methods like this can actually have trouble exploring spaces like that, because it's kind of like explore the parameter space, and sometimes you can like miss that point, and so it's actually hard to try to converge to regions which are really peaky. There's also issues sometimes with, you know, like people sometimes there's these 15 parameters, and you know, like we get these posteriors, and people try to make, you know, like deductions from these posteriors, but sometimes we don't even trust our inferences themselves. So there's actually been some papers on some events where different groups have come, analyzed the same data using the same waveform, but gotten different answers. So that's not good, right? Like, you know, like you'd expect that, you know, our Bayesian inference pipelines would, you know, converge to have the same answer regardless of, you know, who's doing it. And so kind of like convergence tests that, you know, we were talking about with the NR simulations. Yeah, so there's a lot of limitations to Bayesian inference, but it's also like a really good tool that we can use to try to like actually estimate these parameters. I think right now there's also a lot of people trying to do things with machine learning to try to estimate the parameters with machine learning, but I think that the community still hasn't quite accepted these approaches yet. It seems like we're still leaning towards this type of method.
There are
Okay.
several other questions.
Okay, how many iterations do you usually use? Okay, so the iterations depends on some of these sampler settings and depends on the data. So it can really vary. So one of these settings, the N live, is kind of like you can imagine what's happening is that you have like imagine that you have a box, right? And imagine you have a 2D grid, like our, you know, linear regression example. And what NLive does is it's kind of like just throws down like points. These are the number of points you're throwing down in your grid. And you allow them to walk and, you know, like move around that parameter space and try to then create boundaries of regions which have like similar looking likelihoods. And then you go through a process of seeing which ones have the, you know, like which ones have found the least likelihood versus the ones that have the most likelihood. And you then check out those points, and then you kind of you iterate through that process of like checking out bad points and accepting new ones which are better. And so it really depends on like, some of these settings. So if these settings are high, then you could use a lot of iterations to actually go through your parameter space and make sure that all your points are, being accounted for. And yeah, it depends on some of the other things like the data and the priors and stuff like that. So if it's having a tough time exploring the parameter space, then you'll probably end up using more iterations. That's actually one of the downsides of nested sampling as well, because like you don't have a good estimation of when the analysis could end. I remember during the pandemic, we were trying to analyze one of the LIGO gravitational wave events for when it came out, and we were trying to use quite an expensive waveform, and it was taking like several weeks, even using like several using supercomputers. So it really depends on like how you set up your problem. Okay. Could you share some references on the fast likelihood computation? Kate, maybe I'll share those references later. Yeah, I should have probably included them in the notebooks. I'll make sure to like share them with you later. Okay. For the reduced order modeling one, I know the author of that one. That's Rory Smith. For the heterodyning likelihood, I think that it was like one of the first papers in which it was using gravitational waves might have been from the IAS group. Okay. Would the tempering scheme be useful in identifying peak posteriors? Yeah. So people have looked into using like samplers which have which incorporate tempering. So Bilby in fact has an interface to switch out this with one of those, which is called PTMC. So I think that's the one of the MC samplers which incorporates tempering. Cool. Okay.
So
I guess
Renate asked, time for a break.
Okay, yeah.
I need a coffee, sorry.
Yeah, all good. Yeah, let's take a break. I was not paying attention to the time, so.
So let's do a 5-minute break, and then you finish, and then we'll see where Chris is.
Yep. Okay, so cool. So we just stopped at trying to plot our posterior. So here we have our M1 and M2 constraints, and it's like it's pretty jaggedy. It's pretty jaggedy firstly because of the sampler settings we used. We used very few things like live points and stuff like that. But at the same time, we have been able to kind of constrain the posterior around the true value. And okay, I guess this is a kind of contrived example because of all the hacks we use to try to get this. But I just want to show like an example of how you can actually do inference. So if you wanted to actually run this injection yourself, in a more astrophysical scenario, what you can do is you can basically still delete all of this, and you should have your more astrophysical scenario there for you, because then you'll be using all parameters. They'll just take a much longer time. You need to fix that, and you'd also need to, like maybe remove these settings, allow them to be the default settings, which would be a bit more robust. Cool. And let me walk us through the plots. I'm just adjusting my Zoom window. Okay, so here we have our coordinate plot, and in here is a plot of here. Sorry. Yeah, here is a plot of our posterior signal that we've inferred from our parameter estimation, plotted on top of the white constrained data. And this is the signal plotted on top of the in the frequency space. So in this case, again, it was a contrived example, but it's good that, even in the contrived example, we were able to get the right answer. Okay, so any questions about these plots or stuff that we've spoken about so far?
Yes, Avi, that mean reconstructed, what is that in the ASD plot?
Yeah, so what we've done here to generate this is we've kind of just taken our posterior samples and we compute the waveform for each of them. And then we compute what the mean is for all the waveforms together. So it's if we go back to our linear regression example, it'll be easier to see the code for this one because I think it'll make more sense. Sorry, just bear with me first. Okay, yeah, so this is we've done the similar thing here. What's going on here is that we have some samples. So in our case, is the posterior samples. And then what we do is we generate the signal for each of those posterior samples. So this is going to be an array of however many posterior samples you choose to use for this plot. In this case, we're just using 30 samples, but in that gravitational wave case, I think we use the entire posterior file. So we generate the waveform for each of those samples, and then we compute what the mean of that entire list. So we kind of shrink the list into the mean, and then we also compute what the 0.5 and the 0.95 percentiles are. So these are going to be the upper bound and the lower bound of your posterior. Does that kind of make sense?
Yeah, that makes sense for the model. And you're doing exactly the same thing for the signal.
Yeah, it's a bit okay. We can take a look at the code if I'm not sure. Okay, yeah, let's take a look at the code.
If that distracts from the whole thing, just don't worry about it.
I think we have time, right? It's I think we have some time. So okay, so it was, sorry, I'm just trying to bear. I'd helped code this up, so I should know how I'd done it. It was, yeah, here. Okay. So what we're actually doing is Okay, so we grab our samples from the posterior. Let me know if I'm going too fast. Okay, so we grab our posterior samples. We only take n of those posterior samples, and we grab some extra stuff about the plotting. Okay, we recreate our waveform generation tool. Okay, this is plotting the ASD. Okay, here. So now what we do is we generate the waveform in the frequency domain given the posterior samples. So we do this in a loop. We then also inverse FFT it to get what the time domain strain would be. And then, yeah, then we're essentially just doing the same thing. So we have these two lists, the frequency domain list and the time domain list of the waveform. And then we take the, oh, sorry, not the mean, right? It's a median we constructed. Yeah, sorry. Yeah, so we plot the median of those waveforms. And then we get the percentiles of the 95 and the 5 percentile. And we kind of use that for the upper and lower bound. Does that make sense?
Yeah. Thanks.
Okay. So now let's actually work with some real data. Let's try to do the analysis for GW5914. So again, we do some loads, and this time I'm just like loading just the functions to make the code look a bit cleaner. We set up our interferometer again. So this time we're using real data. So this line here, this goes to to one of the packages to actually get like the trigger time of the event. So there is this package that actually, I'm not sure if it's available outside LIGO collaboration, but like you can basically use this to even get the trigger times for the new events that are like being uploaded as the observing run is proceeding. So this is kind of how we use to try to do our analysis as the observing run is on. We then set up some stuff to do with like from when to when we want to get data for. So because we know that GW5914 is a kind of a short signal, we're only going to get it for we're only going to grab 4 seconds of data, and we're going to grab it given the trigger time. We're going to start like 3 seconds before the trigger time, and we're going to allow there to be like 1 second after the trigger. Because yeah, so we download this data. So I think I just ran this. Yeah. Now what we can do is, now that we have this data, we can start plotting it. So did not run this. Okay, so this looks kind of nonsense, right? It's not the pretty picture that we normally expect to see when we plot the strain from a gravitational wave GW5914. And that's because right now this is just the actual raw data. We haven't cleaned it or anything, and so it's kind of really noisy, and it has a bunch of these like high frequency oscillations as well in it. And so we need to actually try to clean it a bit before we can actually see the signal. And but before doing that, let's actually grab the data for the PSD. So in the previous case, we used the PSD that was already like pre-generated and based on the design sensitivity of the detectors. But in this case, what we can do is we can actually generate the PSD using the averaging method that I spoke about previously. So what we do here is we're saying that we want to get the PSD data from the start time of the from the end of the signal plus 28 seconds. So that's how much data we're going to get, and then we're going to chunk these up and then try to actually generate the PSD using that data. So we're using the median Welch method to generate this PSD. Cool. So now I think we have this, And did I run this? Oh my gosh, I'm a mess. Should have done this earlier. Okay. Okay, so we've now gotten the data for the PSD. So we can now try to plot the PSD itself. And what I'll also do is I'll plot some lines, and I'll color the region where, you know, we in a way trust the data very well. So I've colored this green region is from the 50 to 250 hertz region. And these black lines represent two very common noise lines. So these are the violin modes, I think. So the orange line that we have here is the ASD. So that's generated from this method here, like taking the median of all these data chunks after the trigger. And the blue is the actual data that we're going to be analyzing. So does this make sense? Do people understand why the orange is like less noisy looking than the blue? Okay, yeah. Yeah, because we take the median, we're kind of like trying to get rid of any like random like glitches and stuff. That's where we take the median and not the mean. And so this is for the Hanford data. This is for the Livingston. And now what we can do is we can use this information in the, you know, those regions. So we can now take our initial raw data, we can band pass it. So that's kind of just telling it to like only use the data from this frequency range. And we can notch out those frequencies that we don't like. So we can notch out the 60 and the 120 hertz. And then we can replot our raw data. And so there we can actually see the signal a bit better now. We can see that there's something going on, something happening here. And you might have seen this before, but I think these were the settings that we used to actually make the plots in the 150914 paper. We can also make some spectrogram plots. So these are plots in the frequency domain. And so these are some like this is one of my favorite plots of this event. It takes a few seconds to compute. What this is doing is that this is taking the raw data, and it's taking like a it's basically just doing the FFT of the raw data. And then again, we're saying that we only want the data from the 20 to 500 frequency range, and this is the resolution. And so this is what we can actually see the that chirp, the gravitational wave chirp, in the raw data, which is kind of cool. Cool. So moving on, let's set up our priors. And so again, you know, like this time, instead of using, you know, like the default prior, we actually use a narrower prior. So you can see that the chirp mass is between 25 to 31. And sometimes we do this based on, you know, like how, but I think that like ideally we should be like, you know, like using completely uninformed priors. But, you know, if you have some like prior information from about the signal, like if you know the signal is supposed to be 4 seconds long from like the search algorithm itself, then you can try to, you know, use a prior that's meant for a 4-second signal rather than like a really wide prior. Like you wouldn't want to use like a very low chirp mass for a system that has, you know, a 4-second duration. Does that make sense? Okay, I assume it's all good. And again, to make this analysis a bit faster, we're setting some delta functions and we're further narrowing the constraints. Okay, let's plot some prior samples for these priors. Oh, here. Okay, so we've taken some samples. We've taken 10,000 samples, and these are some plots of the priors. Okay. So we can see that these look like TV static, and that's because this is just like just like a uniform prior, and the A2, which is the spin magnitude on the second black hole, and chirp mass, and This is again uniform. There's something going on the edges, and we see that the chirp mass is cutting off down here, and that's like that's okay. It's based on our prior choices again, and so our prior looks like it's decent. And so now what we can do is we can also generate some additional parameters from this. So our priors are actually in chirp mass and mass ratio, but what we can do is we can actually compute some additional parameters, and we can plot the priors for those as well. These aren't priors that we're sampling over, but these are kind of just conversions of those parameters. So this is what the prior samples would look like in the mass 1 and mass 2 space. There's kind of like this kind of cutout in the mass 1, mass 2 parameter space. And this is the histogram of chi effective, which is kind of like the effective spin in the along the z-axis, along the axis of the orbital angular momentum. So we actually like have like a high preference in this type of prior when we assume that the spin can be in any direction. We actually have a high preference for the chi effective to be near 0. So we have a lower preference for these highly spinning kind of systems based on the way we set up our inference problem, our priors, sorry. Okay, so now we can again do our inference. So we create our waveform generator like we did previously. We create our likelihood like we did previously, and then we instead of doing sampling again, we're just going to download my pre-sampled result from yesterday. Another thing I want to point out is that we have these additional things here, additional arguments here. So there is this argument: time marginalization, distance marginalization, phase marginalization. So what this actually means is that we're in the likelihood itself, we're going to use a likelihood in which you don't actually need to sample in time, distance, or phase. So this is using a likelihood in which these can be in a way ignored until the very end of the run. So you can use like one fixed value for these, and at the very end of the run, then you can add these back in. So it's a speed up in your analysis because you don't have to sample over these additional parameters if you set these to true. So this is just another trick to make your inference go a bit faster. Okay, so now that we've loaded the results, we can make our usual plots. And so you can see what your mass ratio is. We think it's like around like 0.8, 0.9. We can see that the chi effective is basically like centered around 0. We can see the masses are whatever these masses are. So we've successfully run GW5914 analysis for GW5914. Okay, so in the last few minutes, I'd like to talk about how we can actually access analyses from previous from the GWTC. So the GWTC is the catalog of gravitational wave events that the LIGO-Virgo collaboration publishes. And they have Zenodo releases every few months after the observing runs are completed. Sometimes it takes longer than what they want. So I think it's supposed to be every 6 months after the observing run finishes, but sometimes it takes longer. And so you can take a look at the Zenodo, and the Zenodo kind of stores the posterior samples for these events and the different models that have been used to analyze these. So here we're going to download data for a particular event, GW 200308. And so this is kind of just the URL to the Zenodo data for this. And it'll take a few seconds to download. And what we're going to do after that is we're going to try to make some plots and look at like how it's actually stored. Does anyone have any questions till then? Okay. Okay, so now that we've downloaded the result, we can load it in, and we can print out some of the stuff that's stored inside of it. So we can see that there is, like these, it's this file with some data stored in IMR, phenom, XPHM, mixed in SUBNR, V4PHM. And so these are essentially just different, like these two are two different waveforms that were used to analyze this particular event. And I think this is like kind of like a combination of both those waveforms in one posterior file. Each waveform has some different physics that was used to actually create the waveform itself. So I think IMR phenom XPHM is a waveform that's a phenomenological waveform that includes things like higher order modes, higher order harmonics of the gravitational wave, and includes precession, stuff like that. The SUBNR family is a family that like models the compact objects effectively using like a one body system. So they keep one body fixed and they watch how the other one kind of orbits that one body. And this also has information on precession and higher order modes. Right now, neither of these actually have any information on eccentricity. There's a different waveform that people use for eccentricity, but then that one doesn't have any information on precession. So it's actually hard to include all these different types of physics into one waveform. People are working towards this, but I don't think it'll be ready by the next observing run. Okay. So let's take a look at what's actually stored inside this, this file. So we see that it has posteriors for all these different parameters. And so some of these we've already spoken about. Some of them are new. Like this cost tilt 1 infinity only precession average. I'm also not sure what that means. I think this is a posterior that's generated by back evolving the binary. So you can take your binary and you can like back evolve it to like a really far away time and see what the spin angles are at that time. Okay, so now that we have these, we can try to make some plots. And so here I'm going to try to load in the chirp mass posteriors from this particular event, and I'm going to try to plot them. And so we see this kind of weird distribution. So we see that both SUB and XPHM actually have different types of posteriors, even though they've analyzed the same data, and that's because they're using different physics. That's basically the main chunk of what I wanted to talk about for parameter estimation with gravitational waves. So hopefully you all now have a kind of like a understanding on how we can download the data and like actually try to sample the parameter space in order to get our posteriors and what some of these different parameters are and all intricacies with like all these different types of waveforms. Does anyone have any questions about any of these pipelines or procedures or on how the LVK actually goes about analyzing the events as they come out?
Yeah, first of all, thank you very much, Avi. I think this was a very fascinating tour through the pipeline. For me, who has no idea about statistics, this was really very informative.
Oh, I'm glad. I was concerned that would be a bit too technical and not that fun when you can't actually run it yourself in person, but I'm glad that you got something out of it.
Yeah, so let me just repeat Avi's questions. Are there any questions from you guys? As Avi, I think this means that everything is good. Okay, if there are no questions anymore, I want to take the opportunity, because this is now the official end of the school. I want to take the opportunity to thank a couple of people. So first of all, I need to thank all the speakers for participating and for giving very good presentations. I think we had quite a broad spectrum of talks, and I think we got a good overview of the area. So thank you very much to everyone who gave a talk. I also want to thank the Auckland crew who made all of this possible, really. So that's Rosemary, Renate, and Richard, the 3 Rs, and Frank in particular, who ran this entire Zoom session and is the technical person in the background. So thank you very much, Frank. I have to thank the Otago crew. That is Leanne, Malisha, Marie-Louise. That's the people who were organizing the travel and the financing and all this. I also have to thank Matt Perry, who is also at Otago. The main thanks I have to give to the funding agencies, and that is the Catalyst Seeding grant that I have received, which is actually funding most of this summer school. The idea of this seeding grant is that one establishes collaborations, and in our case, the collaboration that I wanted to get started was collaborations across the Tasman with people in Osgrave, and I hope that this is a good starting point. This meeting or this conference, online conference that Elliot has announced earlier might be the next good second step. The other funding agency is the Marston Fund, who funds this the Council Marston grant that funds some of the researchers here. Not to forget, I want to thank every one of you who has actually participated, who signed up, who showed interest in this, and I hope you did get something out of it. If you did, then leave your comments on the website that or on the page that Frank maybe can put the link up again. If you did not get anything out of it, then also leave your comments and tell us why. I think that's all I have to say about giving thanks. I just want to also mention that as you have seen, the lectures have all been recorded. We still have to decide where we want to put them, but we will put a link on the summer school website so that you can, if you want to, listen to the presentations again. Yeah, so that's all. The lab is next. I think we'll have a break of maybe 10 minutes or so and reconvene at 40 after 4 or 20 to 5. And hopefully that goes well this time. All right, thank you very much.